Hello. Here we'll deal with probably most important concept in linear algebra, in standard linear algebra class, or rather, three things: coordinates, basis, and dimension. The idea behind all this is that we can if we can identify our vector space with a coordinate vector space, with a vector space of coordinate vectors, by a linear isomorphism, then for all practical purposes, the vector space is just the same as coordinate vector space. So whatever we can do in coordinate vector spaces, we can do in that vector space, just modulo that identification. So the formulation, more or less formal, it's still informal. Coordinates in a vector space is nothing but an identification, but more specifically linear isomorphism between this vector space and the coordinate vector space of some dimension. And then it will be dimension of that vector space. And if we can have it, then we have coordinates. And usually that's what comes first in all practical applications. We see coordinates first, and then we can formalize them by saying that there is a basis behind them, and then all what follows, and then the number of coordinates is a dimension. But let's make it, let's tell the whole story. So first, this linear isomorphism is easier to look at in reverse. Again, an isomorphism is not just one map, but a pair of mutually inverse maps. So easier to start with coordinate vector space and seek an isomorphism with, say, our vector space of interest, this V. And what should happen if we have such an isomorphism? So let's just unpack the conditions of having such linear isomorphism with a coordinate vector space. So what happens in the coordinate vector space, that any vector we can write uniquely as a linear combination of coordinate basis vectors. So these vectors where all entries but one are zeros are standard basis. That's what basis is coming from, the idea of. And then the coordinates in the coordinate vector becomes coefficients in the unique linear combination of basic vectors, making us the answer what we start with. That looks more or less useless. Why to do that if they're already visible in the vector? But the reason for doing that will become clear. So now if we have an identification like that, now if we have an isomorphism between coordinate vector space and some other interesting vector space, what happens is that the value on an arbitrary vector, because f is linear by linearity, we can write that value as a linear combination of the values on basic vectors, on coordinate basic vectors. So I'm doing several moves at once. I'm applying f to this sum, and f is additive, so I can apply f to each of the summands separately and take the sum of values, and then each of the summands is scaling of a vector, and then f is transparent to scaling, giving us this result. So now if we just call the values, these values, some names. They are vectors in our vector space V. So these vectors will have a very special property that for any vector in the vector space V, since F is an isomorphism, we can always find unique coordinate vector which is equal, which is mapped to this V. So for any V, there is this coordinate vector, and it is unique, which is mapped into V. It's just because we have an isomorphism, we can really see this as the F inverse of V. Easy peasy. So what happens now is that any vector V can be written in this form and then expanded as a linear combination, unique linear combination of these special vectors V1, Vn. So V becomes a linear combination in a unique way of our special vectors. Such systems of vectors are called bases. There are usually many bases in a given vector space, if they exist, because it's just how we choose this identification. We can usually choose it in infinitely many ways. So that is really a formal definition of a basis, that any vector in a vector space is a unique linear combination of that collection of vectors. A basis is a collection of vectors, and if it has this property, if a collection of vectors has this property, it is called a basis. And moreover, the number of basic vectors, so bases are arbitrary, some very much arbitrary features of a vector space. We can change them, we can choose them in arbitrary ways, but what will be invariant is the number of vectors in them. So this number n is called the dimension of the vector space V, and it doesn't depend on the basis we choose. The proof we already had when we talked about inverses of matrices. So let's assume that we have two different bases. One is of n vectors, and the other is of m vectors. And both are bases in the same vector space. So in the vector space, every vector can be uniquely written as a unique linear combination of n vectors in this basis and of m vectors in this basis. Then if we look at what we have two maps really. We have a map from Rn into V, and then we have the inverse to that isomorphism from V into Rm. So let's look at this map. And this map will have to be given by matrix multiplication, but we also have its inverse. So reading inverses in the opposite way, we'll have this. So we will have G given by multiplication of matrices with a matrix, say A. G inverse will transform an M vector into N vector in the multiplication with matrix form as well. So the sizes, dimensions of A will have to be M by N, and here we'll have to see N by M matrix B. And then the fact that they are inverse, mutually inverse maps will mean that the products of matrices in both possible orders will be identity matrices. So this will be the identity matrix of size m by m. This will be the identity matrix of size n by n. That is just as usual when we have two mutually inverse maps. They compose, giving us identities, and that is a matrix form of that condition of invertibility. But we saw before that inevitably imply that sizes are the same. And so dimension is an intrinsic number associated with a vector space. If there is a finite basis, then the number of basic vectors in the basis doesn't really depend on our choices, on the choices we make constructing it. So just an example of calculating dimension, finding a basis. Let's look at the space of matrices of size m by n. Then if we look at such a matrix, so a matrix is a vector here, an arbitrary vector m, and then if we look at what it is as a matrix an array of numbers, m rows and columns. So we have m times n matrix entries, and they're all independent. They don't talk to each other, so they must be these coordinates. And indeed, if we just turn them one by one, as we say did here, looking at the coordinates in the standard coordinate vector, and making them all zero, but keeping just one non-zero. If we do the same with matrices, we will end up with m by m times n special matrices, which will be zero everywhere, but one in position at the intersection of ith row and jth column. So these are called matrix units. And any matrix can be uniquely written as a linear combination of matrix units. So a matrix M is, I will write it as a sum, as a compact sum, is a sum of matrix units with coefficients which are just matrix entries. So if I have Mij matrix entries sitting in this matrix, they are just these coordinates. So that is a basis. But as I was claiming, coordinates come first. Basis appears when we look at coordinates and single one, just one of them, and turn all other off by making them zeros, and keep this one being one, and then we will have our basic vectors corresponding to this coordinate system. And then finally the formula for the dimension. It's just counting the number of coordinates, counting the number of basic vectors. It is a product of m and n. See you later.